Our project is officially called Using Big Data to Assess Ecohydrological Resilience Across Scale. But we're quite happy with our nickname, Big Data. In this project, we have a lot of different teams, and they all do something very specific, but they all collaborate, and this makes this entire project work. In the title of the project, there's a couple of important terms, and one of these terms is resilience.
All human beings are familiar with plans changing and problems happening. Some wrench gets thrown in the gears and everything goes wrong. So from an ecological perspective, when we say resilience, we are talking about how easily and quickly can the ecosystem respond to those changes. Does it completely get knocked off course and transform into something new? Or is it able to recover or stay the same in the face of that change? About 3/4 of the Earth's land surface has directly been disturbed by humans. The human footprint globally is enormous. So it's really important to understand which ecosystems, which parts of the land and water in the Earth system are resilient. Even if we modify them quite a bit, they can still maintain that ecosystem health.
It is said that in data science in general, data scientists are spending 80% of time to cleanse the data, to prepare the data, and only remaining 10 to 20% on doing actual work. Let's automate the process of data cleansing. The best way is to use some kind of machine learning technique. And immediately when people thought of that idea, immediately introduced this cycle. We use machine learning techniques to cleanse this messy data so that this cleansed data can be used to do machine learning research.
In recent years, with the advent of sensors, we're now collecting high-frequency water quality data, something like on the order of every 15 minutes over several years. And that now qualifies as big data, and we have a challenge ahead of us. The traditional statistical methods are not very well suited to these high-frequency big data sets of environmental data.
A lot of our environmental processes happen over episodic and short time intervals. So immediately following a rainstorm, our rivers and watersheds become really dynamic in terms of erosion and transport of chemicals and nutrients in the river. So we really care about getting a detailed understanding of what is going on during these event periods.
How the critical zone interacts with these disturbances is very complex, and that makes it very difficult to predict. Our approach is to use data, big data, to extract patterns, and then couple this to the use of process-based models and process observations, and then iterate to get at this process to pattern, pattern to process.
Fortunately, our newer techniques and the increasing computational power that we have available to us in recent years enables us to wrangle those or harness those big data sets and look for patterns in that data that are useful to describe some of the underlying processes that are ongoing.
I love developing new machine learning tools that help humans overcome these kinds of challenges, hopefully to improve their understanding of natural systems, how to maybe manage or better manage the Earth's resources. As a species, our superpower is actually the desire to kind of create meaning. So for me, this whole idea of pattern recognition is just a part of what makes us human. When we do that, I feel like we're all being scientists every single minute of the day.
Some of the most important disturbances that are impacting ecosystems today are drought, wildfire, recovery from acid rain and deposition, as well as changes in precipitation, in particular increasing frequency of these very large precipitation events that can cause flooding and other infrastructure damage, where we have these specific disturbances in mind and are trying to understand their impact on ecosystems, use the data to tell us something about how these systems are responding to disturbances.
Process-based models are really important to be able to sort of try and sort of do some experiments in ways that we couldn't manipulate a landscape in real life. We want to see what might happen if fires occurred more often or if droughts got hotter and longer. These are things that you really need to have all the processes in there, both to be able to capture what's going to happen and then be able to understand why you think they might happen. You need field observations to be able to, first of all, have inputs to put into those models, and then also have observations that you can calibrate and validate your models against so that they're representing reality and then make sure that they're working.
Process-based model can give us the capability to go beyond one individual site. I would call it data-based imagination, I guess, into the future. Like, what's the projections going to be? It can help us go beyond particular location and particular time, and that's powerful.
When I think about the critical zone, I'm thinking about who gets to investigate this idea of the critical zone and who might feel left out or not included. And the same question for me comes up thinking about the history of this term and this construct. Who created, or what group has created this concept of the critical zone? And are there other ways of interpreting and thinking about what's going on this thin layer that we're considering on the Earth's surface?
Critical zone science comes out of geoscience, and geoscience has been dominated by mostly white male perspectives in the past. I think a lot of white leaders and white scientists, myself included, are walking blind spots with respect of the impact that white supremacy has. It will take a lot of intentional work to make changes there and to really also show up for the next generation.
A crucial goal of this project is to really make sure that the content related to critical zone and more importantly, the research findings will make its way into the K-12 environment, but also is impacting researchers in very significant ways. The questions that they're asking, the implications of the research that they're doing, and the ramifications and the effect on society overall.
That's the thing that surprises me a lot about scientists in general. I include myself as a scientist. A lot of scientists don't see beyond their own science. But the practical aspects of that is this science has to be used for something. Otherwise, it's a waste of time. It's useless. I'm always thinking of the end user. How can the science be used more effectively? How can more people be involved in the science? How can we reshape that science? How we really just define science.
The great thing about science is while you have all these different areas, at some point they all connect. That's the great thing. And if you're only in your own little bubble, so then you can't see how it affects the other scientists, the other teachers, and then those students that we're trying to ultimately reach. When it comes to geoscience, most of the time they've only seen white males. And no one has been able to tell them, hey, this can be you someday. What they're learning becomes more meaningful, and it's something that they can go back into their homes, and then it spills over into the community. And this would be a way of helping to engage the community and strengthen the community as well.